Let's talk about another type of sensor, that is optical fiber sensors. So what actually is an optical fiber sensor? That's a device that detects events or changes in physical quantities and provides a corresponding optical output. Or it can be defined as a device in which an external stimulus or a measurand like temperature, pressure, strain, etc. modulates an optical signal, which when demodulated yields the precise quantitative information about the measurand. That is basically, it means that the various physical parameters like temperature, pressure, strain, etc. now we have to study in terms of light signals. So either there will be a change occurring, in the physical quantity, and it will provide us a new optical signal or an output, optical output, or it might be possible that there already exists an optical signal and a change in pressure or temperature, maybe it actually modulates the existing optical signal, and this modulation, when you demodulate it back, you get the proper quantitative information about that particular signal. So optical sensors we can divide into two categories. One is extrinsic sensors, one is intrinsic sensors. Now extrinsic sensors are where the light leaves the transmitting fiber to be changed before it continues to the detector by means of the return or receiving fiber. And in intrinsic, the intrinsic sensors are different in that the light beam does not leave the optical fiber, but it is changed while still contained within it. So over here, like you can see in the figure, if from the source the light travels through the optical fiber, and at some point before being actually received at the detector end after being modulated, if at some point the signal or the light actually leaves the optical fiber, it comes out, gets modulated, and then again it is captured by the detector and it travels through the optical fiber. That is called extrinsic. That means somewhere in the middle of the path, the light rays, they actually come out of the optical fiber and then get modulated. And in intrinsic, through and through, right from the source till the detector, there is a continuous supply, there is a continuous connection of optical fiber, and the light actually does not leave the optical fiber at any point of time. Okay, so while being within the optical fiber only, the external parameters like temperature, pressure, etc., they modify some of the other parameters of light. So extrinsic is where the light rays actually leave the optical fiber and then get modulated. Intrinsic is they get modulated while being within the optical fiber. Now, just to brush up the basics, some common terminologies that we use in terms of light. Polarization. Now, a light wave that is vibrating in all the planes or more than one plane, we call it unpolarized light. Okay, polarized light waves, they are light waves in which the vibrations, they are occurring in a single plane. So you can see that a general light wave actually has variations or vibrations in all the planes, all possible planes. When you put a polarizer in between, and if you see the output, you can see that there is only vertically polarized light coming out of it. That means the vibrations are only in one particular plane. Okay, and this particular process of transforming the unpolarized light into polarized light is called polarization. Then another very popular terminology that we use in terms of light is refractive index. Now, the refractive index of a material is actually a dimensionless number. It actually describes how fast light travels through the material. The formula is N is equal to C upon V, where C is the light in vacuum, speed of light in vacuum, and V is the velocity of light in that medium. So since both the quantities C and V, they are both in terms of velocity, so N becomes a dimensionless quantity. Okay, for example, the refractive index of water is 1.33, meaning that light travels 1.33 times as fast as in vacuum as in water. Okay, so increasing refractive index corresponds to decrease in the speed of light in that material. If your now speed of light in vacuum is actually constant. Okay, so if you have to increase n, So V has to be decreased. Okay. So that means if higher the refractive index, that means lesser is the speed of light in that particular material. Okay. So the refractive index, it determines how much the path of light is bent or refracted when it is entering a new material. So whenever the light rays, it strikes a boundary of two different densities, then two different materials, there is refraction taking place. And how much refraction it takes place, that is governed by Snell's law for refraction. That is N1 sine V1 is equal to N2 sine V2, where V1 and V2 are the angle of incidence and refraction respectively, and of the ray crossing the interface between the media of two refractive indices, that is N1 and N2. So you have two separate mediums. One has refractive index N1, one has N2, and when light travels through it, the light will get refracted, or it will get deviated from its normal path when it enters the second material, and that will be governed by the Snell's law. N1 sine V1 is equal to N2 sine V2. So the refractive indices, they also determine the amount of light that is reflected when reaching the interface, as well as the critical angle for which the internal reflection, their intensity and Brewster's angle. So with the help of Snell's law, you can actually calculate the total internal reflection angle. That is, at what angle we should incident the ray so that the complete light gets reflected back. All these things you can actually calculate with the help of a refractive index. So the refractive index can be seen as the factor by which the speed and the wavelength of the radiation, they are reduced with respect to the vacuum values. Okay, the speed of light in the medium is V, in any medium is V, that is equal to C by N, and similarly the wavelength of that medium is lambda naught upon N, where lambda naught is the wavelength of light in vacuum. So this implies that vacuum has a refractive index of 1, and that the frequency of the wave is not affected by refractive index. So now this is, you can also consider this as a home assignment, that you have to prove using these two formulas of V and lambda and F is equal to V by lambda, that basically the frequency of the wave is not affected by refractive index. Okay, so as a result, the perceived color of the refracted light to the human eye, which depends on the frequency, is not affected by refraction or the refractive index of the medium. So meaning to say that the when from one medium to another medium, when it is traveling, the color of the light actually does not change. Okay, the color that is seen by human eye, that does not change, because frequency does not change. Frequency of the light does not change. It gets refracted, its path gets deviated, but the frequency does not change. Okay, so the refractive index, it varies with wavelength. This causes the light to split into constituent colors when refracted. This is called dispersion. We have all seen this formula. This is observed in prisms, rainbows, chromatic aberration in lenses, etc. So light propagation in absorbing materials can be described using a complex valued refractive index, the imaginary part that handles attenuation, while the real part accounts for refraction. So for most materials, the refractive index changes with wavelength by several percent across a visible spectrum. So refractive indices are for materials are commonly reported using a single value n, typically measured at a wavelength of 633 nanometers.